Hello and welcome to Lecture 2 of Kinematics in 2D. At the end of last lecture, we had a little bit of a look at projectile motion, and we're going to take a much more detailed look at it in this lecture. We've already seen from video analysis that in projectile motion, the acceleration points down, and also we've seen that it's constant, and you'll see this in more detail in the lab. So let's think about a consequence of that. Here we see a long jumper, and we see a final and an initial velocity, and there's the vector subtraction to get a delta v. Now you can rearrange that like so, and you might say, well, so what? Well, if you break the final velocity into its component vectors, and you break the initial velocity into its component vectors, and remember that delta v is straight down here. If we've imposed xy axes in the usual way, then one thing to notice is that the initial and final x component vectors are the same. So this is something that's a very important property of projectile motion. The x component of the velocity is constant. So in the last lecture, we looked at these two different motions, me walking with the mass on the spring and also the projectile. And one thing to notice is that we can think of each of them as a combination of two motions. The mass on the spring you can think about as the mass going up and down on the end of the spring and simultaneously being carried along to the left by me at a constant leftward velocity. And it's when you combine those two motions that you get this shape. Similarly, you can think of projectile motion as a combination of two motions. And the thing to notice about them is that the acceleration is down, and in fact it's g, which we met before when we were talking about free fall. Projectile motion is just another example of free fall. It's simply when free fall isn't along a straight line. So the vertical component of the motion is going to be uniformly accelerated motion because there's a constant acceleration. But since g is straight down, that means there is no horizontal component to the acceleration vector, and that means that the horizontal component of the velocity vector is going to be constant. In other words, the horizontal component of the motion is constant velocity motion. So we have two motions combined. One is a uniformly accelerated motion vertically, and the other is a constant velocity motion horizontally. We already know what the graphs of those two types of motion should look like. Constant velocity motion always gives you a straight line position versus time graph. Uniformly accelerated motion gives you a position versus time graph that's a parabola. And so that's what you'll always find with projectile motion. And now when you combine those, you get this resulting trajectory. And I'll just say, a lot of students seem to associate the word trajectory with projectiles. It isn't. Trajectory just means the path followed through space by any object. And so in the particular case of a projectile, the trajectory is a parabola. But a trajectory can be basically any shape. And just look at this and think about what these different pictures mean. These two, the x versus t and the y versus t, are graphs. They really are graphs. They're abstract. There's no way to see this with your eyes. These are expressions of how x varies with t and how y varies with t. But now this one here, even though I've drawn it as a graph, it is really a picture of the motion. This is what you would see with your eye in terms of the path followed through space by the projectile. So we have uniformly accelerated motion here, and so unsurprisingly the UAM equations that we met back in the 1D motion unit of the course are going to make a reappearance. And so here I've written them out both for the x component of the motion and for the y component of the motion. They're the same equations. I'm just replacing x's with y's everywhere over here. And what we now have is that we have a special case of these. So think of them separately. In the y component, all that's going on is that we know what ay is. It's either g or negative g, and that or is because this depends on how you define your coordinate system. If you set positive in the y direction to be up, then ay is going to be negative g. But if you set positive in the y direction to be down, then your acceleration, your y acceleration, is g. Now, in the x component, we have a 0 acceleration. And so you should realize that these equations are going to simplify radically. However, I'll point out that physicists are extremely lazy. Physicists want to memorize the fewest things possible. And so I would encourage you to be lazy in the same way that physicists are and not even bother to remember that there are this other set of equations for dealing with the x component of the motion. We have a perfectly good set of equations, the UAM equations, that appear all over the place, and just realize that when you put in ax equals 0, they're going to simplify. And don't worry about how, you can always do it on the fly as need be. So we can't ignore that there's a vector nature to all of this motion, and I just want to show you that the way we're going to deal with it may not look always like we're doing vectors, but it is. So think about inventory control again. So in the morning, the fruit in the store is 18 apples and 12 oranges, and during the day there's a shipment that arrives, great big shipment, with all of 12 apples and 6 oranges. And also during the day there are purchases of 7 apples and 8 oranges. So it would be perfectly reasonable for the inventory control manager of the store to write this equation that the fruit in the evening is the fruit in the morning plus the fruit in the shipment minus the fruit purchased, and that comes out to this. Right? Simple. Yeah, well, only a physicist or a similarly ridiculous person would ever think to do it this way, treating the apples and the oranges together in one equation. It's much more likely that the apples and oranges would be tracked separately in a spreadsheet or some inventory control program that does this automatically, looking at UPC codes or whatever, right? But it comes down to the same thing. This evening inventory column is being calculated from the morning inventory plus the shipment received minus whatever is purchased. And so the important thing is that even though you can treat these together, it's more practical to think of them separately. Well, the same thing applies to projectile motion. We could just write a UAM equation like this, right? So here's our second UAM equation, but I've written it all in terms of vectors. And so what we're thinking of here is that xi can be thought of as a vector like so, and vi can be thought of as a vector with its x component and its y component, and a can be thought of as a vector with its x component and y component. And you can collect all the I hats and j hats to express the final position like so. Now, if you find that intimidating and ugly and you really don't want to do it, well, great, because that's not how we're going to do it. You can, but I wouldn't encourage you to. Because remember that all that's going on with vectors is that we have to treat the x components and the y components separately. And particularly in projectile motion, that's convenient because they act totally independently. And so instead of writing a big ugly thing like this, you can just split it out and work with your x components and somewhere else work with your y components separately. So this is what we're going to do in the next lecture. In the next lecture, I'm going to basically work examples and look at how we apply these methods And the thing I want you to notice is that I always split everything into the x components and the y components, and I track them totally separately. The one thing that ties them together is the time.